Hello everyone, welcome back to Deterministic Optimization. We'll continue our discussion on convex conic programming. This is the last lesson in this module. So we're going to introduce a new cone called semi-definite cone, or positive semi-definite cone, sometimes called PSD cone for short. This is one of the most important, if not the most important, nonlinear cones. And we'll see this positive semi-definite cone embodies so many nonlinear, linear, convex optimization. It's really the sort of the broadest class of convex optimization problem that can be solved efficiently. By that I mean the semi-definite programming using the PSD cone. All right, so in order to introduce positive semi-definite cone, we need to introduce what is a positive semi-definite matrix. Okay, so everything in this lecture is going to be about matrices. Before this, we always talk about vectors. Now we're going to talk about matrix. Before we talk about vector being a variable, now we talk about matrix being a variable. So we'll talk about positive semi-definite matrix first. A positive semi-definite matrix is always a symmetric matrix of n by n symmetric matrix. And it has following properties. So A is positive semi-definite if and only if the eigenvalues of A are non-negative. Because A is symmetric, all the eigenvalues of A are going to be real numbers. So we can talk about their being negative or non-negative. To be positive semi-definite, all the eigenvalues of A should be non-negative. Or equivalently, x transpose AX, if you evaluate this quadratic function over any x, that function value should be non-negative. That's an equivalent definition or property of being positive semi-definite. Another characterization is A can be factorized as D transpose D for some matrix D. Okay, so if A satisfies any three of this, then A is positive semi-definite. And vice versa. If A is positive definite, then A satisfies all three, any of them. So this is a complete characterization of A being positive semi-definite. For example, identity matrix definitely is positive semi-definite. In fact, any diagonal matrix with positive or non-negative numbers on the diagonal is a positive semi-definite matrix, because all these numbers are actually the eigenvalues of A. So identity matrix has eigenvalue 1 and 1, and this has eigenvalue 2 and 1. So these are all positive semi-definite matrix. And this non-diagonal matrix, 2, 1, 1, 1, is a symmetric matrix. This also is a positive semi-definite matrix, because you can check positive semi-definite here means the diagonals still have to be non-negative, and the determinant has to be non-negative. So 2 times 1 minus 1 times 1 is 1, is non-negative, so this is positive semi-definite. These two are not positive semi-definite. So if you look at this diagonal matrix has a negative component on the diagonal, or this symmetric matrix has a negative diagonal element, then these are not positive semi-definite matrix. So what is positive semi-definite matrix, positive semi-definite cone? Well, the set of all positive semi-definite matrices is put together of the same dimension. So if you look at all n by n matrices and you pick out all the positive semi-definite matrices of n by n dimension, that set is denoted as Sn plus. S means symmetric. So this is the positive semi-definite cone. Of course, you have to convince yourself this is a cone and it's convex. And it's very easy to convince both. If X is, you pick any matrix in the positive semi-definite cone, then all the eigenvalues of X are non-negative. And if you scale X by a non-negative number, a scalar here, then the scaled version will have a scaled version of the eigenvalues. So the eigenvalues of alpha X are alpha multiplies of the eigenvalues of X, therefore also non-negative. So alpha x is also in the positive definite cone. Therefore, this positive definite cone is actually a cone. And y is convex. To show this convex, you just you take any x and y, two matrices. They are in the second order cone, in the positive definite cone, and you look at their convex combination. You see if their convex combination also is in the positive definite cone. And to test that, it's easier to use the other definition to say the convex combination is lambda x plus 1 minus lambda y. And then you look at this quadratic function of take any x, transpose this new matrix x times x. This is equal to, you can just multiply out as lambda times x transpose big xx plus 1 minus lambda times x transpose big yx. Because x and y are both positive semi-definite, then these two quadratic terms are positive semi-definite, are non-negative, and so therefore their convex combination is non-negative. Therefore, lambda x plus 1 minus lambda y is positive semi-definite. So that shows the second order, the positive semi-definite cone is convex. So Sn plus is a convex cone. Unfortunately, positive semi-definite cone is actually a very high dimensional object if you count the dimension, because Sn plus are matrices of n by n dimension, but they are symmetric. So you only need to look at the upper triangular part of the matrix. Those are independent variables, and whatever in the lower triangular part will be equivalent, identical to the upper triangular part. So n by n symmetric matrix will have n times n plus 1 divided by 2 elements. These are all the upper diagonal elements. So Sn plus is a dimension n plus 1 times n divided by 2 dimensional space. It is pretty high dimension. The simplest one that's coming out is n equals 2. N equals 1 is not interesting at all. So n equals 2 is interesting. N equals 2 is the 2 by 2 matrices. And 2 by 2 matrix, positive semi-definite matrix, has 3 independent components. Let me write it here. So x, y, y, z. Right? This is a 2 by 2 symmetric matrix. This symmetric matrix is in the positive semi-definite cone here. That means we have a 3-dimensional object, a 3-dimensional cone. And you can actually plot this 3-dimensional cone. If you plot it in the 3-dimensional as x, y, and z, and then what you plot, you have to say this thing here, matrix is positive semi-definite. That is equivalent to say x greater than or equal to 0. The diagonal has to be non-negative, plus the determinant. Let me write it more carefully. X times z minus y squared should be greater than or equal to 0. So that is the constraint for this matrix being positive semi-definite. And I leave this as an exercise for you to actually plot this cone. This is the only positive semi-definite cone that we can visualize. All other higher dimension cone is too high in dimension. Okay, so what is linear constraint of matrices? In order to define semi-definite programming, we have to define linear constraint in matrices. It's actually very easy to define because a matrix, although it's displayed as a n by n matrix, array of numbers, you can always think about this as a long vector by stacking the columns of A on top of each other. So, for example, A is this 2 by 2 matrix. It doesn't have to be symmetric, any 2 by 2 matrix. You can think about this as you're stacking the columns 2, 1 on top of 3, 4. So this is a long vector of n squared components, but it's just a vector. We know how to define linear constraint on vectors. A linear constraint on vector is just another vector inner product with this vector. So that's the way we define how we define linear constraint in matrix. It's written as this special way of A times B inner product B is defined as the vector version of A, stacking columns, inner product with the vector version of B. Okay, and that is the same as saying this is the component-wise product and then sum. So that's a linear constraint. This is called inner products between matrices, and this will give us a way to define linear constraint. So let's see, how do we define positive self-definite constraint? A positive self-definite constraint is a linear constraint in a matrix, and then that matrix has to be in the positive self-definite cone. Just like linear programming, we have a linear constraint, and then the variable needs to be in the non-negative orthant, or the second order programming, we have a linear constraint, and then the variable has to be in the second order cone. For a matrix, a positive self-definite constraint, or PSD constraint, we have linear constraint here. This is exactly the same as linear constraint of vectors, and then the matrix itself has to be in the positive semi-definite cone. This is one vector, one linear equality. We can have multiple linear equalities with different coefficients, different right-hand sides, and then x is in the positive semi-definite cone. And this exactly gives us way to define semi-definite program, or SDP. So SDP is a minimization problem of a linear constraint of a linear objective subject to linear equality constraint, and then the variable being in the positive semi-definite cone. So this is the SDP cone. So it exactly has the same characteristic as linear conic programming. The only thing changed is the cone is replaced by positive semi-definite cone. All right, summarize. We have learned what is positive semi-definite matrix, some characterizations, what is a linear matrix equality, exactly the same way you just vectorize matrix and use the linear equality on vectors, and then use that, we define a semi-definite programming. Okay, this is it for this lesson. In the next module, we're going to see concrete examples of positive semi-definite matrix, PSSDP program, and also SOCP, the second order cone programs. Thank you.